Okay, now we will discuss about the impedance of the impedance of a transmission line. Okay, so we have seen one type of impedance, the characteristic impedance. So when you see the characteristic impedance, the significance is already mentioned. So the characteristic impedance basically says that the particular transmission line, if it is terminated with the same value of Z0, so it is very helpful so that you don't have any reflections. Okay, but what we are going to discuss now is a quite different type of impedance. Okay, so what is the type of impedance was, see here, when you move on the transmission line, everywhere, when you move from one point to the other point, you know that the voltage is varying and you know that the current is also getting varying. So when the voltage and currents are varying, your impedance will also gradually vary. So whatever the impedance is observed at the source end, it may not be the same impedance when you reach the load. Okay, so the impedance is also going to vary as a function of distance. Now we will try to find out at a particular value of x, what will be the value of impedance. Okay, it's just only the mathematical derivation part is there. Just one time we'll go through that. So let us try to see. If you recollect what is the equation for voltages and currents, I have given this. The voltage will be the sum of forward voltage plus the reflected voltage. And similarly, the current also I have given the equation. So that is 1 by Z0 V of e power gamma x minus 1 by Z0 VR e power minus gamma x. Okay. So then what will happen to the impedance Z of x right now? That is equal to V of x divided by I of x is equal to, so you can take the ratio V of e power gamma x plus VR e power minus gamma x divided by 1 by Z0 into V of e power gamma x minus VR e power minus gamma x. So take V of common in the numerator and denominator and you can get it cancelled. So what you are going to get Z of x. So Z0 will go to the numerator. And e power gamma x. And when you take V of common from the numerator, so you are going to have VR by VF here. So VR by VF is nothing but your reflection coefficient. So the reflection coefficient you already know. What is the value? ZL minus Z0 by ZL plus Z0. Same thing. So e power gamma x minus. So here also VR by VF is there. So ZL minus Z0 by ZL plus Z0 e power minus gamma x. So what I can do, I can bring out ZL and Z0 terms together. ZL into e power gamma x plus e power minus gamma x plus Z0 e power gamma x minus e power minus gamma x. Same thing. Z0 into e power gamma x plus e power minus gamma x plus ZL e power gamma x minus e power minus gamma x. So correct me if I am wrong. Is it correct? Anything wrong I have done here? Are you there? Yeah. Because if you are not replying means I am getting sleep here. Okay, at least try to make me awake. So to make the answer unaltered, so what I will do, I will divide the numerator and denominator both with divide with 2. So the problem reason was because I can explain this complete term in terms of the hyperbolic functions. Okay, what are the hyperbolic functions you have? So if you remember cos hx, so that can be expressed as e power x plus e power minus x by 2. And sin hx, e power x minus e power minus x by 2. Okay. Now if you look at the first term, instead of x, there is a gamma x. So this can be written as cos h gamma x, and this is sin h gamma x. Okay. So in that case, what is your equation become? Z naught into ZL cos h gamma x plus Z naught sin h gamma x divided by Z naught cos h gamma x plus ZL sin h gamma x. And you can further simplify, take cos h gamma x from numerator and denominator. So you are going to get Z naught into ZL plus Z naught tan h gamma x by Z naught plus ZL tan h gamma x. Okay, this is an equation for the impedance at anywhere on the line if you know the value of x. And this equation can be valid even if the line is a lossy line or a lossless line. This is the generalized equation. You need not be afraid of memorizing these equations, because till now whatever they have asked in the gate, all the transmission lines are assumed to be lossless. Okay, you need not remember this equation, but this equation further slightly modified later, so that is very important. But as I said, right, we cannot predict what kind of questions will be asked in the next upcoming years. So that is the reason why I was telling you all this derivation part also. So this is the generalized equation. So can you tell me what is this value of x represents? Is it from the load or from the source? Yeah, you have to make a note there. So the value of x should be always measured with respect to load throughout our discussion. Yeah. So what is the formula we are getting right now? So z of x is equal to, I will write once again, z naught into okay. Now we will confine our discussion only up to the lossless line. So let us try to concentrate only on the lossless line. So when I say lossless line, you know that gamma value can be written as j beta, because your attenuation will be 0. So ideally speaking, gamma is equal to alpha plus j beta. And when I say lossless line, your alpha value will be exactly equal to 0. So gamma equated to j beta. So in this equation, so if I substitute, gamma will be equal to j beta. So let me write what you are going to get. Z naught into ZL plus Z naught tan h of j beta x by Z naught plus ZL tan h of j beta x. So we know the hyperbolic functions. Oh, tan h of jx is equal to j tan x. Okay. So if you remember that, what you are going to get? So z of x is equal to z naught into zl plus tan h of j beta x. So instead of x, there is a beta x. So the value can be written as j z naught tan beta x by z naught plus jzl tan beta x. So this is the equation you have to remember. Is a terrible equation. Yes or no?
Yes, sir.
Am I making so complicated?
That's Z0, then ZL, then Z0. Again
Yeah,
at bottom
yeah.
Z0, then ZL.
Bottom?
Bottom we have Z0 again, then ZL.
Yeah. No. Am I making my point is, am I making the subject very complicated?
No, sir, no.
See, the thing is, I was making you aware of the subject. There are two ways are there, even you can, some people, I have seen most of the people, they will follow the technique. If you say a very good lecture, they can skip the topics, whatever they know, and suppose they will make sure that most of the people, 70 to 80% of the faculties, in my opinion, what I have observed was, so they will say, or they will explain whatever the topics they know. I mean, if you are getting the answers from the students, means you may think that the faculty is teaching excellent. But in my opinion, it's not like that. So the faculty is the one who makes you that you have to feel the subject is difficult at the same time, and you should know the importance of that. Because after the completion of EMT, if any question asked regarding the impedance, and you should not scold me that time. That fellow has not explained me properly. So many topics he has skipped like that, and all you may comment, right? So that kind of thing should not be done at a later stage. So maybe at this time you may be scolding me for some time, but that's not a matter. But over the long run, you can understand the purpose of it. Okay. So that is the reason why I was explaining. But from the first class only, I told you, when any derivations are there in the discussion, one time you go through that, and after that make a short notes. So I was at a particular point, I was stressing you that this is very important thing you have to memorize. Okay, those formulas you try to include it in a short notes, and you have to do a you have to do the revision on a day basis. So suppose if I tell the concepts now, and if you do the revision after 10 days, you may definitely ask me question, sir, what is impedance on a transmission line? Then it's a very big problem for me. Okay, so whatever the concepts I was telling on this day, if you practice on the same day, by max by the next day, it will be well and good. Or otherwise, it's a problem for both the parties. Okay, don't be afraid in looking at the equations. Just 2-3 times we practice it, and make a short notes and keep on revising it. Every day you just memorize the formulas and try to recollect it. Okay, that way you can remember the formulas. So, okay, we'll go to the next one then. So this is the generalized equation if the line is a lossless. And now there is a question for you. Let me ask you, let me test your understanding. So I have a transmission line of characteristic impedance Z0 and terminated with a load impedance of ZL. Okay, so at what positions the impedance can be maximum? I want to identify at what all the positions where the impedance can be maximum. So can you give me some hint? Can you give me some hint? Whether it is correct or not, you please feel free to share your answers. At Vmax position. Very good, very good. So see the equation. That's why I have written this equation, so that at least you can get some hint. So the impedance will become maximum wherever the voltage is maximum. You already know the reflection coefficient for voltage is equal to negative of reflection coefficient for current. So what is the point? First point you have to remember, wherever the voltage is maximum, at the same position, your current is going to be minimum because of this negative sign. You can see this. If voltage is maximum means at the same position, your current is going to become minimum. And since your voltage is maximum and current is minimum, your impedance is going to be maximum. Okay, so to find out the positions where the maximum impedance happened, that is same as the position where your voltage is maximum. So that is the same formula you can use. So theta plus 2m pi divided by 2 beta. This is the same formula applied for the impedance maximum. Similarly for the minimum also. So the position of the minimum voltage is same as the position of the current maxima is same as, so voltage is minimum, current is maximum. So your impedance is going to become minimum. And you can use the same formula. So what I told for x minimum, theta plus odd multiples of pi divided by 2 beta. So is it clear? You want me to explain anything here? Yeah, okay, no problem. So now, we'll try to find out what is the magnitude. So to find out the maximum impedance, I can define it like this. The maximum voltage divided by the minimum current. So this also can be defined as V maximum by V minimum into V minimum by I minimum. So why I was writing like this one was, you can see this equation, the first one can be written as the VSWR. And the second one, I can call it as a characteristic impedance. Because when you go back to the definition of characteristic impedance in the last lecture, I told you the characteristic impedance is the ratio of net voltage by the net current. Yeah. It can be the forward voltage by the forward current, or return voltage by return current, or it can be maximum voltage by the maximum current, or minimum voltage by the minimum current. So the net voltage divided by the current is basically said to be the characteristic impedance. So your Z maximum is going to define it as Z naught into VSWR. This is your first equation. Okay, so can you do it and me, and what will be the minimum impedance in terms of VSWR? So please do the calculation in the same way and tell me Z minimum in terms of VSWR. Yeah, very good. So Z minimum can be written as V minimum by I maximum. That is V minimum by V maximum into V maximum by I maximum. So the first one can be written as 1 over VSWR. And the second one can be written as Z naught. Okay, so Z minimum is equal to Z naught divided by VSWR. So if any problem is given, you can use these two formulas and to calculate if they're asking about the maximum impedance and the minimum impedance. Okay, I will go to the next concept then. So there is a particular cases where they may be asking you to find out the input impedance. Okay, so what we have seen, we already seen what is an equation for Z of x at any value of x. So let me recollect. Assume that the line is lossless. So this is the equation what we had. So this gives the impedance at anywhere on the line where x is measured from the load. Now you can see the diagram clearly. There is a transmission line and the length of the transmission line is equal to L. So how to find out the input impedance now? So will you agree with me if I say the input impedance is same as Z of X at X is equal to L? Will you agree with my statement? Yeah. See, by the time when you are measuring the input impedance, you are at a distance of L from the load. So to find out the input impedance, that is same as Z of X corresponding to X is equal to the length of the transmission line. Okay, this is very, very important. So the value of Z in can be written as, you replace X with L now. So Z naught into ZL plus JZ naught tan beta L by Z naught plus JZL tan beta L. So this is a formula for your input impedance. Just it's the replacement of X with the length of the line. So you can see here, if you want to find the input impedance means at the source end. So what is this equation says? The first equation, if you look at it, this gives the value of Z of X at any value of X. That means when you move on the transmission line, the impedance will be keep on varying with respect to X. So when you are talking about Z in means you are at the source end. So what is the value of X at this point? When you are measuring the value of X, you should measure it from the load. So when you are at this particular point, you are at a distance of L. So to find out the input impedance, the value of X should be replaced with L. Is it clear now? Okay. So you have to remember here, where L is nothing but your physical length, which is expressed in the order of meters. But if you see the equation, there is one more special term that is called beta L. Okay. Beta L is basically said to be the electrical length of that. If you see the manufacturer specifications, they used to mention the electrical length as one of the parameter for the transmission line. What is the reason behind that was, from the electrical length, you can estimate at what frequency the transmission line can be operated. First of all, you can see the units. So beta is in the order of radian per meter into meter. So electrical length is in the order of radians. So why this is having a very specific significance here was, suppose if you purchase a coaxial cable and they given an electrical length of let us say pi by 2 radians for an example, you can easily measure the physical length with a scale. You take a scale or a tape and you can easily measure the physical length. And if the electrical length is given, you come to know the value of beta because your L value is known. And once you know the value of beta, it can be written as 2 pi by lambda. Okay. So if you know the beta, you will be able to estimate what is the wavelength. So accordingly, you can estimate at what frequency that transmission line is best suited for. So the main significance of electrical length is just to find out at what frequency the transmission line can be effective. So am I sensible? So the electrical length signifies the particular frequency where the transmission line is more effective. Okay, so this is a formula you can use to find out the input impedance. So there are different type of transmission lines are there. So based on the length it will vary, and based on the load also it will vary. So in the next Next, we are going to discuss about what is the input impedance for the different type of lines. Okay. You can see here, this is the formula. Just now I have given the same equation. This is an input impedance, assuming that the transmission line is lossless. So we'll go case by case. So first case, suppose if it is a short circuit line. Short circuit line means you know that the value of ZL is equal to 0, which means that whatever the load I have connected here, the load impedance is equal to 0. In that case, the transmission line is said to be short circuit line. So can you tell me, after substituting the value of ZL equal to 0, what is the value you are getting, input impedance? Do it quickly. So what is the input impedance for the short circuit line you got? Please do that. JZ0 tan beta L. So this is the first case. So this is an input impedance for a short circuit line. Take it as equation 1. So everybody cross check this also and do it for the open circuit line. Open circuit line means your load impedance is exactly infinity. Do it and tell me the value. Z0 divided by J tan beta L. This is your second equation. And there is one more important point to be noticed. So when you multiply the short circuit input impedance and the open circuit input impedance, you are going to get exactly Z0 square. Okay. In other words, the characteristic impedance can also be written as the geometric mean of Are you able to hear me now? Yeah. So the characteristic impedance is the geometric mean of the short circuit input impedance and the open circuit input impedance. So suppose if you have a coaxial cable, if the manufacturer is mentioned that the coaxial cable is having a 50 ohms impedance, you can verify it practically. So in the first case, what you have to do, you don't connect any load at the output. So just leave it as a open. And with you take a normal multimeter, digital multimeter, and you measure what is the impedance with respect to ground. So without connecting any load at the output, measure the input impedance using multimeter. That will give the value of open circuit input impedance. And next second case, what you do, if this is your coaxial cable and the center point and the ground, you just make a short wire. You take a small short wire and short the output of the coaxial cable with the body. And you measure what is the impedance offered at the other end. So you are going to get a short circuit input impedance. So the moment once you take the geometric mean of that using this formula, you just verify whether that data sheet is correct or not. So whatever he is claiming the 50 ohms impedance, is it matching or not? You can practically verify with this formula. Clear? Are you getting my point? Okay, so the next case, third case, let us consider the length of the line is 1/4 of the wavelength. So this is basically said to be a quarter wave transmission line. Okay, so if the length of the transmission line is exactly equal to lambda by 4, first you calculate what is beta L. Calculate what is the electrical length corresponding to that. So beta L is equal to 2 pi by lambda into lambda by 4. So you are going to get pi by 2 radians. So can you tell me what is the input impedance in that case? So substitute beta L is equal to pi by 2. Tell me what is the value you are getting.
Yes, sir.
So you are going to get how much value? Z0 square divided by ZL. Correct? So there is one more important special property is there for this quarter wave transmission line. What is that was? Suppose if the length of the transmission line is lambda by 4 and my load impedance is equal to 0. So if the load impedance is 0, it will reflect the input impedance to be infinity. You can use this formula. If ZL is 0, your Zin is going to become infinite. Suppose if you connect a circuit load and your input impedance reflected will be 0. So what is the meaning of this? If you connect a short circuit load, if you connect a short circuit load here, it is appearing like inputs open circuit. If we connect a open circuit load here, it looks short circuit. So whatever the impedance you have connected here, exact opposite is present at the input if the line length is exactly lambda by 4. So that is the reason the quarter wave transmission line is also said to be impedance inverters. Okay, so why I was calling it as inverter was whatever the load you will connect at the output, it is inverting impedance at the input. As per this equation is concerned. If we connect a short circuit load, it looks like to be open. And if we connect a open circuit load here, it looks to be short here. So the quarter wave transmission lines are basically said to be the impedance inverters. It is inverting the impedance, whatever you connect at the load and when you are measuring at the input. Clear? Shall I go ahead? Yeah. So next case, this you try and tell me. So what will happen when the length of the transmission line is equal to 1 lambda by 2? So I have a transmission line whose length is lambda by 2. So first tell me everybody, what is the electrical length you got? Beta L. Yeah, you are going to get pi. So you can substitute in the equation and tan beta L is equal to tan pi. So what is the value you got? Z in? ZL. Okay, you do the same thing by considering L is equal to 2 times lambda by 2. So if L is 2 times lambda by 2, your beta L is going to become 2 pi. So it doesn't matter, tan pi and 2 pi both will be 0 only. So that time also you will get same ZL. Or not only in this case, if we consider the length is equal to 3 times lambda by 2, your electrical length becomes 3 pi. Now also your tan 3 pi becomes 0 and you will get the same thing. So the condition here is, if you have the length of the transmission line is equal to integral multiples of lambda by 2. So where m is an integer. It can be 1, 2, 3 and so on. If the length of the transmission line is integral multiples of lambda by 2, the input impedance and your load impedance both are same. So those lines are said to be impedance reflectors. So if the length of the transmission line is integral multiples of lambda by 2, whatever the load you are connecting here, the same thing will be reflected at the input. So that is the reason why these lines are said to be impedance reflectors. Lambda by 4 lines are said to be impedance inverters. Lambda by 2 line or integral multiple of lambda by 2 are said to be impedance inverters. Next, last case. This is not so important, but just for the practice you can do it. And consider the length of the transmission line is lambda by 8. So proceed further. So tell me what is the value of beta L in this case? Pi by 4. So when beta L is pi by 4 and you substitute the value, this is tan pi by 4 is going to become 1. Okay, then you substitute what is the value you are going to get. Z in is equal to Z naught into ZL plus JZ naught. Tan pi by 4 is 1. You can leave that. So Z naught plus ZZL. Okay, so I will summarize all these cases in a simple table. So let me put it as a type of transmission line. So all these cases I can summarize it in this table and my input impedance. So first, when it is a short circuit line, you are getting the value will be JZ0 tan beta L. And if it is an open circuit line, you are getting Z0 by J tan beta L. And if it is a lambda by 4 line, which means quarter wave transmission line, Z0 square by ZL. And if it is a lambda by 2 line or integral multiples of lambda by 2, the value will be same as load impedance. And the last one is of, you need not to remember, you can forget it. Z0 into ZL plus ZZ0 by Z0 plus ZZL. Okay. Any questions you are free to ask now before going to the problems. Questions you are free to ask. Shall I discuss some problems then? Okay. So see the question here. So in the diagram, whatever I have given, and consider all the lines are lossless lines. Then find what is the input impedance at this point. So find the input impedance for the following configuration. Assume all the lines are lossless. So if these kind of problems are given, you can name it. So let me say this is my first one, and this is my second one, and this is my third one. Okay, first calculate what is the individual input impedance. Okay, so let me start with the third line. You can see here, this is your third line. So the third line is basically a lambda by 4 line. So when you are calculating the input impedance for the third line, what is the formula? We know. Since it is a lambda by 4 line, this will be Z0 square by ZL. And you can see here, Z0 is nothing but 200 and ZL is also equal to 200. So what value you are going to get? 200 whole square divided by 200, which reflects 200 itself. So that is the input impedance for the third line. So let us calculate what is the input impedance for the second line. So when you see this second line, this is a lambda by 2 line. Okay. Whenever the length of the line is lambda by 2, we just now we seen whatever the load you will connect here, the same thing will be reflected here. So the input impedance for the second line is same as whatever the load you connected because it is lambda by 2. So this is also equal to 200 ohms. Now, so what is the effective load for the first one? So this is your first transmission line. Can you tell me what is the effective load present here? Open circuit? No. You can see the diagram. At this particular branch, there are two branches which are getting out. So you can see that both are in parallel or not. So I can say, very good. Whatever the effective load here is the parallel combination of the second line impedance versus third line impedance. Okay, if you want to calculate the effective load for the first one, it is a parallel combination of the second and third because both are starting at the same thing. So the branches second and third are in parallel. So the effective load for the first one is the input impedance of second line in parallel with the third line. Good. So what you are going to get 200 ohms in parallel with 200 ohms. So when you have 200 ohms in parallel with 200 ohms, what is the value you are going to get? 100 ohms. Two equal resistance are there in parallel means half you are going to get. Now you can find out what is the input impedance here for the first line. So the input impedance for the first line, if you see, so whatever the line I have given, it is a lambda by 4 line. So this is your Z0 and you already defined what is the effective load impedance. So what is the formula? Z0 square divided by the effective load for the first line. So Z0 is 200 ohms and the effective load here, whatever the effective load you are getting it here is 100 ohms. So what is the value you are going to get? 200 into 200 divided by 100. So what is the value you are getting? 400 ohms. Any questions you have here? Yeah. So the same thing, when this kind of problems are given, you start with the rightmost side and try to find out the input impedance for each branch. Then you see the effective load for the first one, whether it is a parallel or whether it is a series. Once if you know the effective load for the first one, you can straight away use the formula to calculate what is the input impedance. So just for practice, let us consider one more example also. You can understand it better. There are the following lines are operating at a frequency of 3 gigahertz. Then find out what is the input impedance. So this is your first line and this is your second line. Here the length is straight away given, right? It is in the order of some 2.5 centimeter or 5 centimeter. Okay, let us try to express this length in terms of the wavelength. So for that, so what is the frequency given? 3 gigahertz. So calculate what is the wavelength. Everybody calculate what is the wavelength first. 3 into 10 power 8 divided by f. F is 3 gigahertz. So you are going to get 30 centimeter. I'm sorry. Yeah, 0.1 meter, which means 10 centimeter. Okay, so when it is 10 centimeter, so 2.5 centimeter is 1/4 of the wavelength. So indirectly I given the first line is lambda by 4. And if you see the second line, this is a 5 centimeter, so which is lambda by 2. So this question indirectly I have given. So based upon the frequency, you calculate the wavelength and then you can express this 2.5 centimeter and 5 centimeter in terms of wavelength. So the first line is lambda by 4 and the second line is lambda by 2. So can you tell me how the first line and second line are connected? Is it in series or parallel? Correct. When both are connected in series, will you agree with me if I say the load for the first one is same as the input for the second one? Since both are connected in series, so can I say this one? The effective load for the first one is same as the input for the second one. Okay, now you can do that. So what is the input for the second one? Since the second line is lambda by 2 line, whatever the load you will connect here, the same thing will be reflected. So if you connect a 100 ohm, here also it will reflect a 100 ohms impedance. So Z into is same as the load for the first one is same as 100 ohms. Okay, then in that case, what is an input impedance for the first line right now, primary line? If you see the input impedance here, and the first line is lambda by 4 line, the effective load impedance is 100 ohms. So Z0 is 100 and ZL is also equal to 100. So you can apply the formula Z0 square divided by the load for the first one. So your Z0 is also equal to 100 and ZL is also equal to 100. Yeah. You are going to get a value is equal to 100 ohms. Okay. So anyhow, we'll stop here and we'll continue with the problems in the next class. Okay. And we had in the next lecture, we are going to complete the syllabus of transmission lines. And after that, there is a waveguides and antennas. So maybe you can expect around another, excluding this lecture, you may have another 10 hours of lecture. I mean 5 sessions, maybe probably there for completing the whole EMT. So in the next lecture, maximum I will try to complete transmission lines and I will start the introduction for waveguides also. Maybe after that 3 sessions it will take for waveguides and another 2 sessions for the, sorry, 1 session for the antennas. So maybe hardly we'll have another 9 hours of lecture, I can say, left over. Okay, now we can ask any questions if you have.